In the last lecture, we talked about the concave mirror, how the image is formed. In this lecture, we will talk about convex mirror, the image formation by convex mirror. This is much simpler than concave. Now, we know that the characteristics of the image depend on the object location. What exactly is the size? Where exactly is it located? All of that can be found without drawing any ray diagrams, which is by the mirror formula. So we'll be talking about the formula that connects image distance, focal length, and object distance. And also there is a relationship between focal length and radius of curvature, that is F equal to R by 2. Then we'll also talk of the magnification formula that tells us the ratio of the height of image to the height of object. Using mirror formula and magnification formula and F equal to R by 2, we can find out every single thing about the image without having to draw ray diagrams. But a word of caution. All of that is based on a sign convention. The numbers, image distance, object distance, even focal length and radius of curvature, they are not mere numbers. They have a sign associated with it, plus or minus. If you make a mistake on that, then we get all wrong answers. So it's very, very important to know the sign convention. And then we'll talk of the uses of convex mirror. Welcome to the portals of real learning. Enjoy your learning. In the last session, we learned about image formation by a concave mirror, and we saw 6 different positions, and we saw how the image characteristics were changing. We had a table, we had an animation. Now let's do the same thing for a convex mirror. This is much simpler. There are only 2 positions. One is object at infinity. What happens? All the rays are parallel. The one that is hitting the pole will go back. Therefore, the image should be on the principal axis. If I take this ray, it gets reflected like that, and all the reflected rays seem to come from the focal point. So the image is formed behind the mirror at the focal point. That means it is virtual and erect. Behind the mirror, rays are not actually intersecting, and it is highly diminished because a point image is being formed. That is position 1, and there's only another position, second, no more than that. Any other position, not infinity. So I take one ray from A parallel to the principal axis, gets reflected, seems to come from the focal point, and another ray I'm taking which is directed towards the center of curvature. It is perpendicular, so it will return back. Extending the ray backward, we find that the position of A is here, A dash, and the image of B will be at B dash, so A dash B dash is the image. The location is again behind the mirror between the pole and the focal point. Size is diminished, it is virtual and erect. That means a convex mirror always produces a diminished, virtual, and erect image of the object, irrespective of the position of the object. Of course, if the object is at infinity, then the image is highly diminished. Otherwise, it is simply diminished. That means what? If you look at the trend, if the object was at infinity, then the image was at F and highly diminished. As you bring the object closer, the image moves from F towards the pole. And in this case of a virtual image, as it comes closer to the mirror, the image actually becomes bigger. In the case of real images, we found that if the image is farther away from the mirror, then it is larger. Here it is just the reverse. And you can handle all of this with the mirror formula that we are going to discuss later. It becomes very simple. So the table for the convex mirror is only 2 positions. It is always virtual and erect. It is always diminished. highly diminished if the object is at infinity, otherwise diminished. The image is either at the focal point or between the focal point and the pole. These are the positions for the convex mirror. What is the use of a convex mirror? One is the field of view. Remember, field of view for a plane mirror, if the object is here, then we had the field of view indicated by this region over here. But if it is a convex mirror, then you see the red arrows. They are forming the big field of view. And therefore, in the side view mirror of our cars, we have a convex mirror. The mirror that is inside the car, somewhere above here, is a plane mirror, so that we can gauge the distance of the vehicles behind us. Whereas this convex mirror is to give us a wider field of view so that we can see what vehicles are there on the other side. And there is something written over here. It is written that objects in the mirror are closer than they appear. Why do they say this? It's because the image is diminished and we are accustomed to thinking that if we are seeing a small object, it must be far away. What we are seeing here in the mirror is the image, right? And the image is diminished as compared to the size of the object. So we tend to believe that it is far away, but it is closer than what we think. That is why they say objects in the mirror are closer than they appear to be. So, summarizing concave versus convex. Concave is made by silvering the outer part of a hollow sphere, so reflection takes part from the inner surface. The reflecting surface is the inner one. In the convex mirror case, the reflecting surface is the bulging surface, that is the outer one. Concave mirror is a converging device, convex mirror is a diverging device. In a concave mirror, the image formed by it is real or virtual. There are five positions where the image is real, and there's one position where the image is virtual. That means it can create inverted or erect images. For all positions of the object at or beyond the focus, the image is real. But if it is between the focus and the pole, the image is virtual. In the case of convex, the image is always virtual for all positions of the object in front of it. In a concave mirror for an object away from the center of curvature, beyond C, the image is diminished. For object at the center of curvature, the images are the same size, and for an object within the center of curvature, that means closer to the mirror, between F and C, the image is magnified. In the case of convex mirror, the image is always diminished. So, very important to remember that a convex mirror never magnifies, it only produces diminished images. A convex mirror, it always produces erect and virtual images, whereas a concave mirror can produce real or virtual images, inverted or erect images, and diminished or magnified images. There's a big difference between the two. Remember this. And this is a very, very good conceptual question. How can we tell the difference? Suppose the question is we are given three mirrors. One is a plane mirror, one is a concave mirror, one is a convex mirror. How can we tell which is which without touching their surfaces? If you touch the surface, you can make out that it is plane or like this or like this. You can make it out by touching it, but you're not allowed to touch it. How can you make out which is plane, which is concave, which is convex? Well, stand in front of it first of all, or hold the mirror without touching it. Hold the mirror in front of you and see your face in the mirror. Okay, then if the image is erect and the same size, then it can only be plane, because concave mirror, when it produces an erect image, it always magnifies it. Whereas a convex mirror will create an erect image but always diminished. So if it is erect and same size, it must be a plane mirror. But suppose you find it is erect, but you can't really make out the size, whether it is the same size as the object, then move the mirror a little farther. That means you are increasing the object distance. Just move it farther. If the size of the image doesn't change, then it is plane mirror, because the size of an image in the case of a plane mirror doesn't depend on the object distance. So it is erect, but you can't make out whether the size of the image is more or less than the size of the object. So just move the mirror a little bit farther. If the image size doesn't change, it must clearly be a plane mirror. But if the image size increases, then it must be concave. And if the image size decreases, it must be convex. How do we say this? That is the interesting part of this question. And I'm going to show this to you as to how we can say this by using a diagram. Just to complete this argument, if the image was erect and same size, then clearly plane mirror. If you can't make out the size, then move the mirror a little bit farther and then decide based on what you observe. On the other hand, if the image is inverted, it must be concave. Plane mirror will never produce an inverted image, and convex mirror also will not produce an inverted image. Now, how did we do this? Look, if the image is erect, and suppose it is a concave mirror, then clearly we know that the object must be between the focal point and the pole, right? That is what we are discussing. So if it is a concave mirror, then the object distance is less than the focal length. And I'll tell you why I put this moduli. I'll tell you why we do this later. But right now, just understand that the object is between the focal point and the pole. So here is the focal point, here is a concave mirror, and the object is placed here. Let's complete the ray diagram. One ray goes like this, parallel to the principal axis, hits the focal point and goes away. Another one hits the pole, obeys the laws of reflection and goes away. These rays are diverging. By producing them backwards, we are able to find the image position. Okay. Now, we move the mirror a little bit farther. Equivalently, we move the object a little bit farther, but still within the region of F and P. So if I move it farther, then the new object position is just O dashed. I draw the same ray parallel to the principal axis. It again goes to the focal point. Second ray, which is hitting the pole, now the angle of incidence is smaller than the previous one. And therefore, when you produce this ray backward, it is hitting it here and the image has become larger. So, this ray diagram clearly tells you that if you are having a concave mirror in front, you are seeing an erect image. If you move the mirror farther away from you, the size of the image will increase in the case of concave. But in the case of convex, it will decrease. Let's do the same exercise for convex. So I have an object anywhere. It doesn't matter where it is now. For convex, it doesn't matter because there are only two positions. So one ray is parallel to the principal axis, gets reflected, seems to come from the F. Another ray hits the pole, obeys the laws of reflection, goes away. Producing the rays backwards, we find that the image is here. Now let us shift the object farther. Now the object has come here, so this ray is the same. Hits the same point. This ray that is hitting the pole is different. The angle of incidence has changed. So when I produce it backwards, it is hitting this line here, and the intersection point is here. The image is here. The image has become smaller. So in the case of a convex mirror, right, you will see an erect image. If you move the mirror farther, the image size will decrease. That is the logic that we use here. Go back. Go back. If the image is erect and we can't make out the size, then simply move the mirror a little bit farther. If it was convex, then the image size would decrease as we just saw. And if it was concave, then the size of the image would increase. And that is the analysis that we did just now. Very interesting, isn't it? Very, very interesting. Now, let me derive two formulae. One is the focal length is equal to half of the radius. So here is a concave mirror. Although I'm going to derive it for a concave mirror, it is equally valid for a convex mirror. I take a ray that is parallel to the principal axis. It hits this point M and then goes through the focal point. Now, the angle of incidence will be the angle between this ray and the normal at the point of incidence. The normal is a line joining the center of curvature to that point. So this is angle of incidence. I'm writing that as I. That will be equal to the angle of reflection. I'm also calling it I. So this is I and this is I. Now, since this line is parallel to the principal axis and this is I, therefore this is also I. Now, this is I, therefore the external angle is 2I. Okay. Now, one very important approximation that we're going to take, that this M is such that if I drop a perpendicular from M onto the principal axis, hitting at a point P dash, the approximation that I'm making is P dash is nearly the same as P. That means this M is not too high from the principal axis. Okay. And such kind of rays that hit the mirror at some distance above the principal axis or below the principal axis, but not a great distance, small distance, and the angle of incidence is also small. Those rays are called paraxial rays. So only under that approximation of paraxial rays, we are going to derive this formula, not otherwise, not otherwise. If we had a huge mirror and we had a ray coming like this, then this point is very much higher than the principal axis. Then all these approximations don't work. Then if I drop a perpendicular from there onto the principal axis, that won't be the same point as the pole, right? It will only be applicable if this M is not very high from the principal axis. So if I is small under paraxial ray approximation, then we know that I is equal to tan I. And even 2I will be small enough for us to say that 2I is equal to tan 2I. Tan 2I is MP dashed by FP dashed, but that is the same thing as MP by FP because we are taking P dash as nearly the same as P. Then tan of I now is MP by CP. So we wrote all of this, but I can remove this tan because angle is small. Now divide the two. Then I get 2 is equal to MP by FP into CP by MP. So MP cancels. 2 equal to CP by FP. What is CP? CP is the radius of curvature. What is FP? That is the focal length. So 2 is equal to R upon F. Therefore, F equal to R by 2. One very important relationship. Now, this formula F equal to R by 2, or we are going to talk about mirror formula and lateral magnification formula, are all only valid in the paraxial ray approximation. Although laws of reflection are always valid, we don't need any approximation for that. But this formula and the mirror formula, which we are going to talk about, and the lateral magnification formula, they are only under the paraxial ray approximation. Paraxial rays are those that are close to the principal axis and make small angle of incidence with it. Okay. So the mirror formula is this. I'm not going to do the derivation. F equal to R by 2 we just derived. Mirror formula is 1 by V plus 1 by U is equal to 1 by F, where V is the image distance and U is the object distance. But all of this is subject to, first of all, paraxial approximation, and it is also subject to the sign convention. What is a sign convention? First of all, every distance that we are talking about is measured from the pole of the mirror. We start from that pole of the mirror. All right. So if an object is at this location AB, then the object distance would be measured starting from P. But the direction of incident light is like this. We are going against the direction of incident light. Such a distance will be negative. But if there was any distance to the right, it is along the incident light direction. So that distance would be positive. This applies to image distance, object distance, and even radius of curvature, and even focal length. It applies to all such distances. Secondly, any distance above the principal axis is taken as positive. Any distance below the principal axis is taken negative. So all these formulae are subject to this particular important sign convention. If you make a mistake on signs, then you'll get all wrong answers. So that means focal length of a concave mirror is negative. How do we say that? Well, this is a concave mirror. So the reflecting surface is this one. The focal point would be somewhere, let us say here. The focal length, the object would be to the left. The focal length would be measured starting from the point P, and you're going against the direction of the incident light. That is why the focal length of a concave mirror is negative. And therefore, the radius of curvature, because F equal to R by 2, the radius of curvature of a concave mirror is also negative. But the focal length of a convex mirror is positive. For a convex mirror, this is the reflecting side and behind is the silvered side. The focal point is here. This is the pole. The incident light will come like this. The focal length is starting from the pole, we go towards the focal point. This is along the direction of the incident light. Therefore, the focal length of convex mirror is positive, and the radius of curvature is also positive because radius of curvature is the distance PC. That also is along the direction of the incident light. All right. Focal length and radius of curvature also have a sign associated with them. And magnification, lateral magnification is nothing but height of image by height of object. And it is written as M. So suppose the object was this one. This is HO, height of object. And suppose the image was this A dash B dash. That is HI, height of the image. Lateral magnification is simply HI by HO. But in this case, HI is negative because it is below the principal axis and HO is positive. Whatever it is, just apply the appropriate sign convention. And then we find, I'm not going to do the derivation, M turns out to be minus V by U. And M will tell us a lot of things. If this M is positive, what does it mean? If M is positive, M is HI by HO, right? If M is positive, that means the sign of HI and the sign of HO are the same. Either both of them are positive or both of them are negative, right? Suppose both of them are positive, that means HO was positive and HI was also positive. That means image is erect. So if M is positive, the image is erect. If it turns out to be positive, because it's a ratio of minus v by u, if it turns out to be positive, then the image is erect. If it turns out to be negative, then the image is inverted. That is the first. Second, forget about the sign and only look at the magnitude of v by u. If that magnitude is greater than 1, that means hi by ho is greater than 1. That means hi is more than ho. That means it is a magnified image. If magnitude of m, forget about the sign, if the magnitude of m is more than 1, then image is magnified. If the magnitude of m is less than 1, then the image is diminished. And if it is equal to 1, then hi is equal to ho. So m tells you a lot of stories. It can also tell you whether the image is real or virtual. Because moment you know that it is inverted, then you know it is real as well. And the negative sign will tell you that it is inverted and therefore it will be a real image. So M tells you many things. So we'll continue from here, and in the next session, which will be a concluding session, we will do some numericals on the entire chapter.